Okay, welcome back to the first session after lunch. Um, so our first speaker in the session is Titouan Leclercq from Lyon, who's going to talk about Oracle modalities for higher dimensional types.
Thank you. So this is a work with Andrew Swan. Mostly what I did in an internship with him for a few months. So I'll talk about those Oracle modalities for higher dimensional types, which are a way to generalize the idea of oracles in computation uh, in computability theory, but in homotopy type theory, and thus trying to get a tool for higher dimensions, like for one types, two types, etc. So the setting is kind of basic. We have the usual constructions for homotopy type theory. The univalence is not really needed for what we'll do. And we also assume Markov's principle because it's needed for some proofs, which I will not show, but under underneath some use of Markov's principle will be needed. So I formalized a big part of what I'll be talking about, and I didn't send a pull request yet, but it will be on the higher computability library. So first, I'll recall quickly what are modalities, but I mean we already had a few talks about it, so it will really be basic and if you want to study modalities, this talk is not really uh, indicated. So what we will take for modalities are functions with a unit and some conditions that I won't detail. Being a modal for some modality means that the unit is an equivalence, and we write U superscript circ for the model types. This will be mostly used to consider some sub-universe with, for example, some property for its inhabitants. So for what I'll talk about, every modality will be Lex modality. So U circle will be a model of itself of homotopy type theory. So the main modalities we will use, and the only one fact, are nabla and nullifications. So nabla, you can see it as taking the set theoretical world from the universe of types. What I mean by this is that it's the smallest modality for which the law of excluded middle is verified. So you can define it as saying that you want every proposition such that its double negation is true. You want every such proposition to be inhabited. And the nullification, in our case, we will just use it in case of a family of propositions. And we can see it as taking a modality making every such proposition contractible. So more important aspect is computability, which I'll detail some more. So computability is based on in the usual theory on the part of computable functions, which are some partial functions which can be enumerated by what we can see as a universal Turing machine. We just define what we mean by the arrows notation. We also consider machines with oracles. So if we have a function from n to n, which can be non-computable and most often will be, we see phi e superscript f as the code as taking a code of machine which can call f as some black box and which, if we interpret it, we will really take the as like if it calls f of x, it will really take the real result of f of x. So this allows to define the Turing reduction, which is a relation saying that f will be computable using G as an oracle. So it's just this is just a formal expression of this. For two functions, if we say that they are reducible to each other, then we consider that they are Turing equivalent. So this is this relation, and Turing degrees are the class of functions which we quotient by this Turing equivalence. So it's really a notion of how strong a function will be in its computational power. We also have some definitions for subsets of n. So it's computable just when its function, its characteristic function is computable, and it will be computably enumerable when it is a domain of a partial computable function. So this set, which is halting set, is most known computably enumerable set. So it's the set of Turing machine which halts on their own code. And now we'll do synthetic computability. So instead of considering like just before a subset of computable function, we consider that every function is computable. So, for example, the most important example of this is if we work in the realizability in the effective topos, and synthetic computability is really a generalization of what happens if we try to work internally in the effective topos. Here we have a variant where we are not just in the effective topos, but in a model of homotopy type theory, but the idea is the same. But then we need a way to define non-computable functions, because if we want to take an oracle, an interesting oracle, we need to be able to talk about them. So we consider the functions which are from nabla A to nabla B, because as I said earlier, the world of nabla is really the world of set theoretic functions. So every function which are well defined but not necessarily computable will be inside this universe. In fact, we mostly use A to nabla B, which is equivalent. We say that it's defined that such a non-necessarily computable function is defined at some point, when in fact it can be factored through the unit. So if it is really a point of B which we inject in nabla B, and thus the function phi e superscript f will be a function which can consider f to be a real computable function, so which for which f is considered total. And for this, there is really natural way with everything before to formalize it, which is to consider types and function in the world where we nullify the fact that f of a is defined. So this is the starting point of my work, and it's based mostly on Andrew's paper on oracle modalities. So the goal is to generalize this idea of oracle modality. So we'll try to find a way to express what it means to have an oracle for a function, for possibly something else than a function, which can be a type and an higher inductive type typically. So if we just consider the most basic case, which is really what we're interested in computability, it's the case of functions from n to n, and in this case we can see such a function to be a function from n to finite set, and then compose this function by the cardinal. It seems kind of useless like this, but we can generalize this idea of taking the cardinality, because being a finite set can be seen as a particular case of being a finite CW complex. CW complex are kind of the basic internal construction of higher inductive type. So this is a quick reminder of what is a CW complex. We changed the definition a bit because it's easier to talk about CW complex in a way where we add only one sphere at a time, but we can choose the dimension of the sphere for enumeration reasons. So CW skeleton will be a sequence of spaces where each space will be the push out of the space before with some sphere. And a CW complex is the colimit of some CW skeleton, which we don't give in the to make being a CW complex a proposition. And being a finite CW complex is the same, but we just take some finite sequence of spaces. So this gives us what we want for generalization for oracle modalities. So instead of just a function from A to nabla B, we will take a family of sets which are CW fin in nabla. So as I said, nabla is itself a model of homotopy type series, so we can also define what is a CW fin in nabla. And in a sense, such a CW fin will be CW complex in the set theoretical world, but maybe we can't know how to compute such a skeleton. And the oracle modality associated to such a family will be the fact that we can lift this family to some real real finite CW complex. So it will be the nullification of the family of is CW fin. Yeah. So first, it is indeed a generalization, so we can express what we had at the beginning. A small remark is that when we take the function f a to nabla b, and consider the fact that f of A is defined, it's not always a proposition if B is not itself a set. And for oracle modalities, the definitions were mostly made with sets in mind. So we always consider that, in fact, we have even a separable set. And in our case, it is a generalization over functions to sets, but it can also talk about other family. Yeah, so this is our definition of oracle modalities for higher dimensions. And now I'll talk about a computably enumerable set. So another definition, which is more useful, is that we can consider a grid which is computable, and our subset of n will be the limit of each column of the grid. So we can take the grid to be non-decreasing, or just to take the max. I put both, but only one of the two would give an equivalent definition. So this is what happens if we want to construct a set, and we can see it as at each step of time, we decide that we add some elements in our final subset. So when we try to generalize it to higher dimensions, we say that instead of adding an element, we make a push out against a sphere, because if we take the -1 sphere, it will be a push out against the empty type. And so here, if here it is 0 and here 0, the result will be 1. So it will really be the idea of adding a point. But we also want to be able to just do nothing. So this is why in this definition we have the notion of option, which also appeared for the CW, I think. Yes. So it just says that maybe we can just take the next space to be equal to the one before, and such a grid of types with pushouts will be called the C grid, and generalized computably enumerable then type will be the colimit of such a grid. And when we are working with a proposition, in fact, C in the usual sense and GCE are just equivalent. I think it's just it can be seen just with this. We can take exactly the same function, but transfer the 0 and 1 to the types empty and unit, and we can do the same thing if we have from m to m+1. If we do nothing, then we can do nothing. If we take push out and still want to be a proposition, we are only able to have an empty type going to a unit type. So we are doing a push out with the -1 sphere. So for the converse, it's kind of straightforward too. We just construct a grid from such a grid, from such a CE grid. So for sets, it's more interesting because in fact we can alternate between values. So for example, this is a sequence with 1 2 1 2, and we can always realize it in a way with some sequence of pushouts by saying that so we are starting with a point, then we are adding a point which is an obvious operation. We link the 2 points. So this is a pushout against the zero sphere. Yes, I think. So against bool, we by taking the endpoints to be the 2 points and the pushout will add an equality between them. So then it becomes contractible again. But we can then add another point, and we could link this other point to the group of linked points. So in the end, we can always alternate, and the co-limit of such a sequence will be the lim inf for this case with 1, 2 values, because it can be something else if we have just an arbitrarily number of elements in our sets. So this lim inf is in fact a characterization of the sets which are CE with an oracle for the halting sets. And we did not prove that the converse hold. So with this, we know that being a KCE set is means that it is a GCE family of sets, but the converse is still a work in progress. And finally, I want to talk shortly about the case of groupoids. From our construction, it can be seen as just groups, because we can always take apart the connected components. And our construction process will be that we can either add a path, which, if we consider the free group, we will be adding a constructor. And if we take homotopy between some already defined path, it's a relation we add in the group. So it's really a presentation of a group, and an oracle would give a finite presentation of a group. So it's still not really computable when we have the oracle, which is why I'm not sure it would give really the computational strength of computing a group. So yes, we have a generalization for higher dimension, but we still have some questions. Also the fact that so we have CE for propositions, KCE for sets. So maybe for groupoids, the described sets would be some K-prime CE, which would be like the natural generalization of taking the halting set, but we are not sure, and it doesn't seem obvious. So yeah, I forgot the H. Anyway.
We have time for 1 or 2 quick questions.
If you add computability for the loop spaces of the spaces that you add computability for, does that give you more of a computational boost that you're looking for?
So you mean if you add like an oracle for the loop space after taking the oracle?
Yeah.
Yeah, maybe, I'm not sure, but yes, it would. Yeah, I mean, maybe. I didn't think of it, so well, I try to see if it can do something, but yeah, sorry for the lack of answer. But...
Hi, I had a question about the definition on, I think it was slide 10 or 11, maybe. You can go back to the. Yeah, sure.
Yeah.
So I just wanted to check about the truncation. So does it mean that the family is a generalized CE, which is a proposition when like propositional truncation there exists and then data? Is that the right reading?
Yes, it's
Okay.
yeah.
And the same on the previous slide. Ordinary.
Yeah. For this one, no.
No, the next one.
The next.
Yeah.
Yes, it's also
Propositional truncation there exists data.
yeah.
Yeah. Thank you.
Okay. Any pressing final question? No? Okay, then let's thank the speaker again.